Hi, and welcome to this short demonstration of an additive repair workflow using Polygonica. So first of all, just to note, this demonstration program is not a real application, it's just our demonstration program for Polygonica. So the actual product is a software library. Okay, we've loaded in a sort of kind of mock-up of a scan of a worn part that we've created. So this is intended to look a bit like a laser scan in that there's some noise that we have to deal with, and also there's some worn regions. So you can see here it's pretty worn away on the edge, and also here it's worn away on both edges there. So what we're going to do is load in the reference part first of all. So this is the original CAD part, if you like, and we're going to use this to compute which regions are actually worn on the scanned part. So if we go to this new additive or worn part repair toolbar here, the first thing I'll do is use Polygonica's advanced registration functionality. So this is feature-based registration, and it does very, very accurate alignments of two parts together. And you can see that's done a nice job there. And if I make that one transparent, you can see the worn part underneath. And the second step is to compare these parts and compute a worn region. So click that, and we've done that here. We've created a worn region in this, and what we've actually showing is a polyliner or a polycurve on the surface that smoothed and bounds the worn region. So if I just hide the target part there, you can see, for example, in this one it goes quite a long way down, and that's because if we look from the side, you can see it's worn away not just sort of on that axis, but also on this axis here. So the real part should come up and make a right angle, but it doesn't do that. So these boundaries, they're reasonably complicated to compute, and Polygonica, it uses quite a lot of different functionality within Polygonica relating to comparisons and regions and polycurves and smoothing and this kind of stuff. But there they are, and they should be fairly easy, or they are fairly easy to get into your CAD engine or your CAM system or whatever as P-curves, or as you can fit splines to them or whatever. So you can use these as the basis of creating tool paths in a CAM system that you've already got. But here we're going to do that, or at least a proof of concept toolpaths using Polygonica. So if I make this transparent, what I've done is created a milling path based on these tool parameters here, although Polygonica has just basically picked some, or the Polygonica example code has picked some defaults, and we've just created some 3-axis milling paths just to mill away the worn regions. So we've got a nice smooth surface to actually then add an additive toolpath to it. So there we go. I've clicked on that, and that's now created an additive toolpath. Same idea. It's a 3-axis one. You can see that should nicely fill in those regions. And I'm going to export that to the LWN format. So LWN is like a G-code type format that MachineWorks uses just for demonstrations and things. So it's a simple way of getting G-code type operations into MachineWorks, so we can actually simulate and see what these toolpaths look like. So I'll save that. And now I'm going to switch to the MachineWorks demonstrator. So this is another MFC application, very, very old. I originally wrote this in the 1990s, and we've never really upgraded it, which is shameful, really, but there you go. I'll load in this bracket.lwn, and so here's that worn part file. And although I say we haven't upgraded it, you can see it now defaults to using the GPU to do the machining operations, but I'm not going to do that. That's still under development and not yet released, although it's going to be, version 1's going to be released shortly. I'm just going to show you using the VisiCut, which is the standard polygonal engine inside MachineWorks that most people use. And I've used a fairly thick tools here, so I'm just going to run these through to the end because it won't take very long. So there's the milling path, and there's the additive path. And you can see we've filled in those parts. Okay, the additive bead width, or whatever you want to call it, is quite thick here. In reality, it probably wouldn't be that thick. But we've computed that, we've machined that away and then filled in the regions quite nicely, all using Polygonica operations like offset, intersection, and curve offsetting, etc. I'll just quickly show you that more slowly. So let's do, how many cuts are there? 303,000. Let's do every 100 cuts just so you can have a bit more of a look what's going on. So that's the first 100 cuts. So I'll just do by, so that's cleaned that area out, and that's cleaned this region out here. And now we start on with the additive, and you can see it's just adding the additive in concentric offset toolpaths. Okay, so that's the first model. Let's switch back to Polygonica demo and let's have a go at perhaps something a bit more realistic, even though it's still a mock-up. So here we have a turbine blade, and you can see it's typically worn at the edges. So this is something that's a bit more realistic. So again, we've mocked this up. We've taken a model and sort of stressed it, worn it away a little bit, like you might take a new bit of furniture and stress it to make it look older and more chic. And in doing so, we've introduced some self-intersections. So one of the important functions in Polygonica is mesh healing, because if you start your workflow with a model that isn't topologically correct, you can end up with lots and lots of problems with your downstream algorithms, because your downstream algorithms don't know where there's solid material or where there isn't solid material. So Polygonica, I think by now we can say Polygonica is renowned at having very, very good automatic mesh healing. So I'll just click that, and you can see the self-intersections have gone and all the traffic lights down here are green. So we've got a nice model to start with. And I'm going to load in the healed design part. And again, same thing, we need to register these because one's a scan, one's a CAD system. They're not in the same coordinates. So we'll use the feature-based registration. Again, we get a nice result there. And then if I make that transparent, and then let's find the curve around the worn region, and there we can see it there. So again, we can see there's a very thin region that we need to fill in. And this time I'm going to create a multi-axis toolpath, both for milling and for additive. So click that, it takes a little bit longer. So what we're doing here is we're actually offsetting the part and then intersecting it to produce a curve, and then offsetting that curve along the surface. So you'll see, let me hide some of this. You'll see it's not brilliantly, you can't see it brilliantly here, but you can see we've got that the actual toolpath follows the curvature to an extent, and it's a lot more obvious if we actually add the additive toolpath there. And you can see there's a sort of region on top where the tool follows the sort of top curvature, and then as we get to the edge here, it almost creates another set of loops. So if you're on the actual machine, you would probably have it at this sort of orientation here. So you would be tilting the part over and adding material from the top so that it doesn't flow over. But the purpose here isn't to demonstrate toolpath generation, it's really to demonstrate that Polygonica has all the tools that you need for toolpath generation. So we've just knocked this stuff up very quickly. Okay, so let's export that to MachineWorks and see what it looks like. Load LWN, and let's load the part in MachineWorks. Okay, so there's the worn part. And again, I'll just switch it to VisiCut. And let's zoom in a bit so we can actually see what's happening. So zoom in there. And I'm just going to play this through to the end. So there's the milling path, and then here's the additive path adding material on. And again, we haven't paid any attention as to where the material's hot, where the material's not hot, where it needs to be. We've just created a very, very simple toolpath by offsetting the curves inwards. But the key point about what Polygonica is giving you here is the ability to find those, if you like, non-planar slices, and then to offset those across the surface. which is a very powerful and quick way of creating these additive infill toolpaths. And again, I'll just show you, there's the original on top. I don't think I have a transparency option here, but you can see it's pretty close. I mean, we've used, we've not made any attempt to machine this down or anything like that, but it's a pretty reasonable representation of the material, of the volume that needed to be filled. Okay, so that's the end of this demonstration. If you'd like to know more, please get in touch. You can contact us via the contact form on the website, or both websites. MachineWorks has a website also. Or you can find us on LinkedIn. There's a MachineWorks Limited page on LinkedIn, and there are Polygonica and MachineWorks product pages, or you can contact me directly on LinkedIn. So thanks for your time, and yeah, wishing you all the best.